Alright, in this video we are going to be reviewing polar bonds again, and then we're going to be taking that information and we're going to be using it to figure out whether entire molecules are polar or non-polar. So a good spot to always start here is, remember, polarity is determined by electronegativity of the elements in that molecule. So we want to have, a reference or a periodic table that will help us know the electronegativity of these elements to help us out. So I recommend this one, but if you have your own periodic table, that'll work. And then let's do a few practice problems with just polar bonds. So if we got a hydrogen over here and an oxygen over here bonded together, hydrogen has an electronegativity of less than 3. Oxygen's closer to 3.5. Oxygen has a higher electronegativity, so it's going to have the electrons closer to it, giving oxygen a partial negative and hydrogen a partial positive charge. So that would be a polar bond. All right, let's take a look at one more example. In this case, we have 2 oxygen atoms bonded together. So when we have 2 oxygen atoms bonded together, they're going to have the exact same electronegativity. The electron's going to be shared in the middle. And this would be a non-polar bond. So when a molecule is only 2 atoms large, like this one, it'll work exactly the same. So we could take a look here, hydrogen and chlorine. Hydrogen has a really, or not really low, but low for a non-metal. It's got a less than 3 electronegativity. Chlorine is closer to 3, so it's higher. The electrons are going to be shared a little bit closer. Oh, I didn't draw that too good. A little bit closer to chlorine. And when we're drawing our molecules, one way that we show this is we draw it with arrows, and the arrow will point towards the way the electrons will be getting pulled. So we could draw it like this, showing that electrons are being pulled towards the chlorine. And that'll give us a partial negative charge here and a partial positive charge here. And if we ever have partial charges, that will tell us if it's a polar or non-polar molecule. So now we have, partial charges. That is a polar molecule. All right, so that was just like polar bonds because it was just 2 atoms. Let's jump into a molecule that's a little bit bigger. It's got more atoms in it. All right, so for this one, you have to look at each bond. And what I like doing is just starting off with drawing the arrows in what direction the electrons are getting pulled. So if we just take a look between carbon and fluorine, let's start there. Just between carbon and fluorine, carbon has a less than 3 electronegativity. Fluorine is always our highest. Fluorine always pulls those electrons towards it. So the electrons are going to get pulled towards the fluorine that way. Here's another carbon-fluorine bond, so they'll get pulled this way. Here's another carbon-fluorine bond, so they'll get pulled this way. And here's another carbon-fluorine bond, so it gets pulled that way. And then once we kind of have an idea of where all the electrons are getting pulled, we need to draw what we call the dipole moment. So what this is, the dipole moment, shows which direction electrons are being pulled in a molecule kind of as a whole. So the way we do this is we add up all these vectors together. In this case, you can see that they're all getting pulled in opposite directions equally. So if you cancel them all, well, if you add them all up, they cancel each other out. And even though we got 4 polar bonds here, this is going to be a non-polar molecule, because all of these poles are canceling out. All right. If we do, we're going to take a look at a very similar molecule with one difference here. So instead of having fluorine all around it, we're going to switch one of those fluorine with a hydrogen here. And we're going to see how that changes things up. So we said that fluorine has a higher electronegativity. So it'll be pulling electrons out that way, pull electrons out this way, and this one will pull electrons out this way. If we take a look at carbon and hydrogen have a pretty similar electronegativity. So that electron is going to be nice right in the middle there. So if we wanted to now draw our dipole moment, we're going to take a look at what direction these electrons are getting pulled, and then we would draw it in that direction. So if you add all these up, if it's on a two-dimensional sheet of paper, it's going to look like this. Well, I don't even want to draw it that way. It'll draw, let's scribble this one out. It'll be directly towards this F. But if we want to look at it three-dimensionally, it'll actually be right in between all of them. These three fluorine are going to form kind of a triangle, and the pole will be directly between all of them. So on a two-dimensional paper, you might draw it straight towards this F, but in reality, in a three-dimensional picture, it'll be in between all of them. And this will be, if we want to draw our partial charges, this will be a partial negative on this side because that's where the electrons are getting pulled. And our partial positive would be closer to this side near the hydrogen and the carbon over here. And because we have the partial charges, this is going to be a polar molecule. So we'll take a look at one more, and then we got 8 practice problems that you guys can try on your own, and then I'll work through them together with you guys if you need some help. So in this molecule here, we have a lot of different bonds. We got 5 different bonds. We got to take a look at each one. And the more you do this, the faster it gets, because you'll see that carbon and hydrogen, they have a similar electronegativity, so they won't have any, they're a nonpolar bond, so they don't have the electrons getting pulled one way or another. So we got a carbon-hydrogen bond here, carbon-hydrogen bond here, and carbon-hydrogen bond there, all nonpolar, so we don't got to worry about them. Now with a carbon-oxygen bond, we got to think, where is that electron getting pulled? Carbon's got less than 3 electronegativity, oxygen's up here with 3.5. That electron's going to be getting pulled this way. And then with oxygen and hydrogen, very similar. Hydrogen's less than 3, oxygen's about 3.5. It's getting pulled that way. So if we wanted to draw the dipole moment of this, our overall dipole moment would be in that direction. And if we wanted to draw the partial charges, this oxygen would be, partial negative, and then we have a couple partial positives. So this one will be a little bit positive, and this carbon and this side will be a little positive. One thing I want you guys to know, we don't need to know the numbers of these. We don't need to know exact charges. They're just between 0 and 1. If you add them all together, though, it's important to know that those charges add up to 0. So even though it looks like we got more partial positive charges than partial negative, this partial negative is going to be a larger partial negative than either of these 2 partial positives together. So if you add all the partial charges up together, it's always going to equal 0 because the molecule's a neutrally charged molecule. All right, so that's kind of the steps. You want to always look at each bond, whether it's polar or nonpolar, draw where those electrons are going, and then add those directions together to see if they cancel out or if you actually do have a line that the electrons are getting pulled to.